Okay, in section 9.3, we're going to look at Taylor's theorem. So let's start off with an example. And it asks us to approximate a function to certain specifications. So remember, our polynomials will approximate function values, but they're not going to be exact. So to find a Taylor polynomial that will serve as an adequate substitute for sine x on the interval negative pi to pi. Well, excuse me, adequate is kind of a nebulous term. So we are going to choose some polynomial so that the difference between the polynomial value and the actual value of sine x is going to be less than 0.0001 for every x in the interval negative pi to pi. That's pretty accurate, as close as 0.0001. So in order to do that, we're going to make p sub n of pi minus sine of pi less than 0.001. We know that pi looks like this, or sine of pi. So at the function value, or the area at sine pi, is going to be the largest that we are going to get. So this is, wait a minute, this is 0, pi, there we go, 2 pi. So we're going from negative pi to pi. So if we apply sine of pi to this, then p sub n will be adequate throughout the entire interval from negative pi to pi. So p sub n of pi minus sine of pi has to be less than or equal to our 0.0001. Sine of pi is 0. So p sub n of pi, in other words, the polynomial, has to be less than 0.0001. So we're going to evaluate our partial sums until we get to the sum that will give us a value less than that. So if we add this, if you get your calculator out and give it a try, if you do pi minus pi cubed over 3 factorial, we'll do that as you do, get your calculators out. So pi minus the fraction of pi cubed, pi cubed divided by 3 factorial, which is 6, I get negative 2.026120 for my first partial sum. If I add another term to that, which would be pi to the 5th divided by 5 factorial, I get 0.52. So the third partial sum gives me 0.52404. If I keep going, when I finally get to this polynomial, my value is 2.114256, et cetera, to the negative 5th. So 0.00002, which is less than 0.0001. Okay? So we have to just keep adding our partial sums until we get to the one that gives me a value that is very close to sine of pi. So let's take a look at what the next value is, or the next topic is. So the truncation error. In practical terms, then, we'd like to be able to use Taylor polynomials to approximate functions over the intervals of convergence of the Taylor series. And we'd like to keep the area of approximation within some specific bounds. The last one was 0.0001. Since the error, the difference between the actual function and the polynomial, results from truncating the series down to a polynomial, that is, cutting it off, we call it a truncation error. Here's what we're talking about. If I have some polynomial, p of x, where f of 0 is f prime of 0x, this should look familiar, f double prime of 0 over 2 factorial x squared, etc., and then our last term, well, actually, I'm going to write a few more. F triple prime of 0 x cubed over 3 factorial plus f to the 4th derivative 0 x to the fourth over 4 factorial plus et cetera, et cetera. So if I want to use this polynomial to approximate a function value, I can't just keep adding and adding forever. If it's geometric, I can, because I can do a sum of the series, but I'm going to at some point have to truncate it or cut it off. So if I cut it off here, let's say that's accurate enough, my truncation error is everything that comes after that. So my truncation error is the value of all of the values, all of the terms that follow after. So my truncation error is the remainder. This is my approximation. My error is everything that I left off. Now, for an alternating series error bound, we have some specific things. And a lot of what I'm telling you today, we're going to put the pieces together a little bit as we go along, but I wanted to get them into your notes. We're not going to deal with all of this tomorrow, but we are going to deal with some of it. Alternating series. Suppose the terms of a series have the following three properties. These are going to be very, very important. The terms alternate in sign, plus, minus, plus, minus. We've seen a lot of those. The terms decrease in absolute value. Almost anything over a factorial, the bottom is getting bigger quicker than the top. So it is approaching, or it is decreasing in absolute value. And the terms have to approach zero. So as we get out towards infinity, our terms become very, very, very small. If that's the case, then the truncation error after n terms is always less than, alternating plus minus, getting smaller and smaller, the absolute value of the first term that we leave off. So if I do all the terms up to the nth term for my approximation, then the nth plus 1 term is actually a good approximation of my truncation error because the value of this term is smaller than, the entire truncation, if we kept going, would be smaller than this term. Again, get this down. Don't worry about understanding everything because we're going to go back through this. Got one other thing I think to show you, and that is Taylor's theorem with a remainder. So Taylor's theorem. If f has derivatives of all orders in an open interval I containing a, in other words, we can continue to derivate on and on, then for each positive integer n, and for every x value in the interval, this is true. We've already looked at this. We now are saying that somewhere down here will be a remainder that will be our truncation error. And R of n is going to be defined by the nth plus 1 term. So if I truncate at the nth term, my remainder is going to be the n plus 1 term. The first equation in Taylor's theorem is Taylor's formula. That's the one we've been using. The function r sub n of x is the remainder of order n, or the error term for the approximation. So once I truncate and I use an approximation of p sub n, the n plus 1 term is the remainder or the error. It's also called the Lagrange form of the remainder, and it bounds the remainder and bounds on, in other words, limits on this remainder are called the Lagrange error bounds. So again, we're going to be looking for errors within a specific value. So let's look at one example of this. We are probably not going to get to this in the next class, but I want you to get it into your notes. So an example that proves the convergence of a Maclaurin series. So prove that the series, and does anybody recognize this? This is the Maclaurin series for sine x. Prove that this series converges to sine x for all real x, because our interval of convergence for sine x is all real numbers. So consider the remainder as n approaches infinity. By Taylor's theorem, the remainder is this term, where f to the n plus 1c is the n plus first derivative of sine x evaluated at some c between x and 0. For this function, the derivative is always between -1 and 1. We're using sine functions here. So we've seen where the derivatives of sine at c fluctuate back and forth between 1 and 0 and -1. So therefore, the absolute value of the remainder equals the absolute value of the remainder written in our notation form. And that's going to be less than 1 over n factorial times x to the n plus 1. So I've completely eliminated this and replaced it with a 1. That's the maximum value that I can have on this interval for the derivative at c. So I can say that this value, whatever this number is up top, it's going to be less than 1. Therefore, I can use this for my notation. And as n approaches infinity, the factorial growth is much larger than the exponential growth. You need to know that. Therefore, as n approaches infinity, this expression approaches 0, which means that the remainder will always approach 0. Therefore, for all x, my remainder is going to approach 0 and will not affect the convergence of the series. Again, I know that's a lot to take in, but get it into your notes. And again, this is not something we're going to use immediately, but I wanted to get you a good chunk of this content into your notes so that we could start to work with it as we go along.